Welcome to Escape Velocity Space News. I am your host, Dr. Pamela Gay, and I am here to put science in your brain. As comes up now and then, there is a lag between when Erik and I write and record each episode, when Allie gets them edited and pushed to our patrons on Patreon, and when the episodes go public on YouTube. This means I'm recording this episode on October 30th, as I look forward to Halloween and as I dread next week's presidential election. Our patrons will get this over the weekend as early voting comes to an end and campaign ads reach a fevered pitch. And you, our viewers on YouTube, you will get this after the voting has ended and possibly after the next president has been decided. I am currently wishing we produced a weekly show because this past week has been full of news that is surreally relevant to both space exploration and the elections. We've seen Jeff Bezos, owner of the Washington Post, Amazon, and aerospace company Blue Origin, have his newspaper not run a candidate endorsement to protect his federal contracts for Blue Origin. We've seen SpaceX owner Elon Musk seemingly break election law by paying people to be registered voters willing to make certain promises. And we've seen SpaceX continue to break the Clean Water Act, as Elon Musk funds Trump's campaign through a super PAC to the tune of millions of dollars. This is an election where the billionaire aerospace company owners are protecting their interests in ways we've never seen before. I could rush an article on this topic that some of you will see before you vote, but instead, we're going to watch what happens and bring you a longer story once we've come to understand more about the situation. Instead, this week, we're going to look at next-generation instruments for observing dark matter and dark energy. These are being built to explore from on the ground and in space, and we're going to take a closer look at the light pollution optical and radio telescopes on Earth are now having to contend with from satellites, from the mega constellations of communication satellites that have been getting launched this year. And the weird thing is, I have no idea which story will matter more a year from now. The story I am writing on mega constellations or the story I'm not yet writing on billionaire aerospace company owners. We live in weird times. This is EVSN, a product of CosmoQuest, supported through Patreon. Back in 1998, researchers studying supernovae discovered that our universe is accelerating apart. Up until that point, it had been understood that our universe's expansion was either going to slow to a stop, continue on as is-ish, or reverse its motion and collapse in on itself. The idea that the universe could be accelerating apart wasn't even on the list because that would require some new something to exist that is causing the acceleration. And is so often the case, our creativity failed to account for the diversity of things at play in shaping our cosmos. Following our tradition of bad names, astronomers named the unknown thing that is accelerating our universe apart dark energy, even though it may not be an energy. And for the past 25 some odd years, we've been trying to define what dark energy could be and how it can be observed. And 25 years is just long enough for major missions and telescopes designed specifically to tackle this question to be coming online. The big three on our radar are the Euclid Space Telescope from ESA, the Rubin Observatory being built in Chile, and NASA's Roman Space Telescope. The Euclid mission was the first of this trio to get eyes on the skies. Launching July 1st, 2023, it spent its first 30 days traveling out to the Lagrange Point 2, a gravitational sweet point beyond Earth where it will orbit the Sun at the same rate we do. This is the same place where JWST and Gaia Space Telescope orbit. Once in its final location, it began de-icing procedures and calibration, with the first science images being released in May of this year. Those 5 images, while visually stunning, did nothing to help us understand our cosmos. To complete its primary science mission, the Euclid mission will need to image 1/3 of the sky and carefully measure the shapes and distances to myriad galaxies located within about 10 billion light-years of the Earth. This data will tell us 2 key things. 1, by mapping the distribution of objects over time, Euclid will reveal how the large-scale structure of our universe has evolved from a spongy material to the lacy web we see today. 2, by measuring how the shapes of galaxies appear distorted by the gravity of otherwise invisible dark matter, Euclid will map the 3-dimensional distribution of dark matter. Putting these 2 factors together, where dark matter is located, and how the distribution of matter changes over time, we can piece together a more complete understanding of what forces must be working on visible and dark matter across time, and start to understand if dark energy has always existed and always affected the universe in roughly the same way. Euclid will spend 6 years acquiring this data. On October 15, Euclid gave us a sneak peek of what is to come. In a data release that showed us roughly 0.5% of the sky in exquisite detail, Euclid was able to reveal the faint clouds of gas that surround our Milky Way, as well as myriad galaxies, clusters, and all the structures they form together. In the coming months, we can look forward to early analysis of what this amazing data set tells us about the universe. If you want to learn more about Euclid, our sister show, Astronomy Cast, just did an entire episode on this mission. Check it out at astronomycast.com or wherever you download podcasts. Euclid will be focusing its cameras on the parts of the southern hemisphere sky that aren't contaminated by the dust and stars of the disk of our Milky Way. This means its observable region overlaps with what will be targeted by the upcoming Rubin telescope's large survey of space and time. In this complementary investigation, the still under construction ground-based telescope will be observing the entire visible sky every few days from its perch in the mountains of Chile's Atacama Desert. This will allow it to not only measure the cosmic structure, but to also catch all the motions of objects in our solar system and the flickers and flares of objects ranging from forming stars to merging black holes. With science operations slated to start in late 2025, we're finally starting to see major components of this 8.4-meter telescope and its suite of cameras coming together. The 3.5-meter secondary mirror was installed in July, and on October 28th, we learned that a test camera allowed the telescope to finally catch some photons, with first light taking place on October 25th. The test camera has 144 megapixels, which may sound huge, but the planned survey camera will measure in at 3,200 megapixels. This test camera will allow them to put the optics through their paces and to work out any issues in the system before the survey camera is installed in January. Also experiencing final construction is the Roman Space Telescope. Set for launch in late 2026 or early 2027, this infrared telescope will join Euclid at the L2 Lagrange point, where it will perform complementary observations to Euclid and also make observations of planets orbiting nearby stars. Exoplanet observations are made possible by the first ever active coronagraph to be sent to space. This means that we'll have the capacity to block the light from stars with variable characteristics, and it can respond to changing conditions to allow different planets to be observed without their star's light drowning them out. This instrument was integrated into the Roman Space Telescope's instrument carrier in October and will be mounted into the spacecraft at a later date. The Roman telescope will observe the sky in the infrared, and like the JWST, this is being made possible thanks to some special structures that like to cast shade. Also in October, we learned that the spacecraft's outer barrel assembly, which is essentially a long box, has successfully gone through centrifuge testing and is ready for its role preventing stray light from interfering with observations. Or it will be once it too is installed in the spacecraft. Roman still has a ways to go in its construction, but each new milestone gets us that much closer. And maybe, if we're lucky, as these surveys wrap up in the 2030s, we'll start to get a handle on what is pushing our universe apart. After the break, we're going to take a look at a variety of telecom satellites that are making this science harder than we expected when we started planning these surveys. Stay tuned. On October 30th, the Star Walk app on my phone let me know that if I saw a bright train of lights moving across the sky, I was probably seeing the 200th batch of Starlinks passing overhead. While I didn't see that particular Starlink train, I've caught other groups going by, and these low-orbiting satellites put on one heck of a show as they reflect sunlight from orbit back toward our planet. We can only see them in the hours before sunrise and after sunset, but they are there all night long, and when we can't see them by reflected light, they are still causing problems by eclipsing streaks of the sky as they fly by. The Starlink mega constellation of telecommunications satellites isn't the only constellation being built. It was just the first to sneak up on astronomers and make us aware of a new problem we're going to need to plan around. 5 years of Starlink launches later, we're going to take a moment to reflect on the reflected light, radio pollution, and atmospheric concerns being raised with megaconstellations. In old-timey science fiction, communication satellites were placed in geosynchronous orbits where they could relay signals to a set region on our planet and to other satellites in space. From their altitude of 36,000 kilometers, these satellites could be giant stations and still only appear as a faint stationary point of light in our sky. In reality, this works, but the connections are too slow for easy conversations. And as internet speeds increase, the lag introduced by the speed of light is actually getting noticeable. A round-trip signal to a geostationary orbit and back takes 0.02 seconds. To bring us faster internet communications, companies like SpaceX have been bringing telecommunications satellites down closer to Earth and placing them in orbits 340 to 640 kilometers up. By putting them more than 50 times closer to Earth, they can reduce that light speed-induced lag by the same factor of more than 50. To be clear, large, high-power, low-impact on astronomy satellites aren't being used for satellite internet because of our need for speed. What is being done with tens of thousands of low Earth orbit satellites could be accomplished by tens of geostationary and other high-orbit satellites that can provide service to polar regions. While one geostationary satellite can serve the needs of people on a large region of our planet as they sit still in the sky, it takes myriad satellites that streak by in minutes to provide service to those same humans. Starlink alone plans to deploy 12,000 satellites in their network, and they have discussed expanding to 34,000 satellites. And Starlink is just one of the myriad constellations planned by megacorporations and countries around the world. Each of these networks is designed somewhat differently and creates its own unique problem to people on Earth trying to enjoy or study the universe beyond orbit. While ultimately fewer in number, the new AST Space Mobile Bluebird satellites are giant disks of solar panels and antennae that outshine everything else in the sky. Orbiting 500 kilometers up, the 168 spacecraft planned for this constellation can saturate a quarter degree of the sky each. Back in January 2020, at the American Astronomical Society meeting in Hawaii, many of us listened in as astronomers talked about plans to work with SpaceX to create darker satellites that would impact our ability to see the sky a little bit less. The idea was to work together to make it possible for humans on Earth to go out and enjoy a meteor shower or take observations of far-off galaxies without satellites wrecking their plans. The International Astronomical Union even worked with astronomers and satellite companies to create international standards for the brightness of satellites and their radio frequency usage so we could protect our dark and radio-quiet skies for science. In 2022, I tried to observe a meteor shower, and the constant interruption of satellites kept tricking me into thinking I was seeing shooting stars, when all I was seeing was orbiting hardware. Today, the latest generation of Starlinks are the brightest ever. Those Bluebird satellites I mentioned are 900 times brighter than the IAU standard. It is now estimated that every 30-second exposure of 1 degree of the sky will have one or more satellites if the observatory is located between plus or minus 50 degrees latitude. The streaks generated by these satellites could cause observing programs to take order of 10% longer to complete, which doesn't sound like a lot, but in our highly competitive environment, this will mean entire research questions that can't be studied, and more people like me who get frustrated trying to observe meteor showers or other night sky phenomena. And before you say, just use space telescopes, I want to remind you that an 8-meter telescope costs millions to build on Earth and billions to build in space. We simply can't afford to replace all our ground-based systems with space telescopes. Human beings see our universe in optical light. This makes it easy for us to understand how satellites can pollute our astronomical images with reflected sunlight as they pass overhead. The thing is, this is a passive problem. We have a star that shines, satellites are shiny, and thus we see reflected light. In the radio sky, we also have problems, but these are more actively created. While Starlink and other telecommunication satellites are supposed to be using specific radio bands that are controlled under international agreements, they often stray into other segments of the electromagnetic spectrum. In 2023, the European LOFAR radio array found unintended radio emissions in the wavelengths of radio generally reserved for science. Those were first-generation Starlinks. Now, in 2024, they're finding the second-generation satellites are 32 times brighter and potentially exceed thresholds set by international regulations. An article on this problem in the journal Science reads, "Worst nightmare. Elon Musk's Starlink satellites could blind radio telescopes." While we have many different telescopes in space, studying wavelengths from the infrared to the ultraviolet, radio astronomy is largely done from Earth because it requires massive dishes and geometries that are easier to attain on a planet's surface than in space. We can't move our planet's radio astronomy capabilities into orbit with current technology. In addition to optical and radio light pollution, we also need to be aware that objects that we put up in low Earth orbit end up falling back to Earth through our atmosphere. When we put things up in geostationary orbit, they will stay put until moved or hit by something else. The reason for this difference has to do with the Earth's atmosphere creating drag up to several hundred kilometers above the Earth. This means that everything we put in low Earth orbit either will need to be regularly expending energy to stay in orbit, or will need to be replaced every few years. Currently, it appears that both these things will happen, and we're going to see near daily launches of new bundles of satellites and the regular decay of satellites back through the atmosphere. This causes two problems. On the way up, rockets release particles into the atmosphere that can eat away at the ozone layer. And on the way down, spacecraft become particulates that can increase global warming. The issue with the ozone layer is particularly troubling, as models show a tenfold increase in launches by rockets burning hydrocarbons, like solid rocket engines, will increase UV radiation in the northern hemisphere, increase upper atmospheric temperatures as much as 2 degrees, and change atmospheric wind patterns by several percent. The full impact on the climate isn't well understood, and many researchers have been demanding that research be funded before things hit an irreversible point, and calls have been made to slow the rate of launches and delay the licensing of new batches of satellites until we understand what we're doing to our world's environment. As it stands, the income companies can make off high-speed satellite internet and cell phone service is dominating the conversation, and the needs of capitalism are dominating over the needs of conservation. I can report on what is happening. I can report on what science tells us will happen if we continue building out the mega-constellations currently being planned. And I can tell you I don't want to experience that future firsthand. But it is going to take more than just the words of a reporter to keep our skies dark, our radio telescopes able to do science, and our atmosphere safe from rocket exhaust and spacecraft debris. I'd like to leave you with one question. Is this worth 0.02 seconds of internet latency? Up next, Erik Madaus is going to bring us this week's Tales from the Launchpad. Stay tuned. Next up, I'm pleased to welcome on Aerospace correspondent Erik Madaus for this week's Tales from the Launchpad. Hey, Erik.
Hi, Pamela. On October 29th, China launched the crewed Shenzhou 19 spacecraft into orbit from the Xiuquan spaceport. On board was the usual complement of 3 astronauts. Commanding the mission was Chai Zhuxia, who previously flew on Shenzhou 14. The other 2 crew members were first-time astronauts Song Lingzong and Wang Haoze. The spacecraft completed a fully automated docking 3 hours after liftoff. The previous crew, Shenzhou 18, will return to Earth in the coming days after a brief handover period. Shenzhou 19 will spend 6 months in space. We keep track of orbital launches by launch site, also called spaceport. According to Rocket Launch Live, so far this year, the United States has had 112 launches, China has had 52 launches, New Zealand has had 10 launches, Kazakhstan has had 6 launches, Japan and Russia each have had 5 launches, India and Iran each have had 3 launches, French Guiana has had 2 launches, and North Korea has had 1 launch. This makes the total number of launches so far this year 199. Finally, there are 10 toilets in space. Of these 199 launches, there have been 4 failures, reminding us that space is hard.
Thanks, Erik. Before you go, I would like to report on the funniest astronaut story I've seen in a while. On October 28, astronaut Don Pettit's son posted to Twitter, quote, "My family just got served 2 jury summons at once. And as if that wasn't absurd enough, one is for the one of us in space right now." End quote. I know that legally jobs are required to provide workers time off to serve jury duty, but I think the cost of the commute might require this summons to get postponed for now. But like Pettit Frontiers, I really want to know, just what should one tell the judge in this kind of a situation? And that's it for now. We'll see you all on the other side of the election. In the words of Obi-Wan Kenobi, our allegiance is to the Republic, to democracy.